Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So in this video, I'm going to teach you on the first subtopic of the first chapter in SK025, which is the reactions rate. For subtopic 1.1 reactions rate, I have divided it into 6 parts. So we're going to do the first part, which is reactions rate. Reactions rate is defined as changes in concentrations of reactants or concentrations of product as a function of time. Okay, so how do these definitions related to the term reactions rate? Reactions comes from chemical reactions, where we know that we're going to have both reactants and also products. While for rate, we know that chemical reactions require times to form products from reactants, so we need time in here. So to look at these definitions more clearly, we need to look at an example. Given to you these reactions, hydrogen gas react with chlorine gas to give hydrogen chloride gas. So on the left hand side, we have reactants, and on the right hand side, we have products. So as the reactions proceed, we know that the concentrations of both hydrogen gas and chlorine gas will decrease as they are being consumed throughout the reactions. While for hydrogen chloride, the concentration gonna increase as they are being formed throughout the reactions. In order to know the reactions rate unit, we need to first substitute the information given in the chemical equations into the formula of reactions rate. So once we substitute the information given, then we're going to get rate is equal to changes in hydrogen gas divided by changes in time, followed by changes in chlorine gas divided by changes in time. Lastly, changes in hydrogen chloride divided by changes in time. So how do we read this formula? If you can see here, we have different signs, negative and positive. So what does this negative and positive sign represent? So both negative signs located on hydrogen and chlorine gas indicates that the concentrations will decrease with time. As we have discussed earlier, that the concentrations of reactant will decrease over time as they are being consumed. While for the concentrations of hydrogen chloride, they are expected to increase with time as the product is being formed throughout the reaction. So that's why we have positive signs. So will these negative and positive signs gives you the unit? No. As for the unit, we need to look at the numerator and denominator. As for our numerator, we have concentrations. So for concentrations, we can use the unit of mole per liter or mole per decimeter cubic or molar. They are all the same. As for denominator, our denominator is time. We can use either second, minute, hour, day, and year. It depends on the questions. So once we combine these two numerator and denominator units, we will get an example of mole per decimeter cubic per minute. So this is the reactions rate unit. We can also illustrate the reactions rate graphically by using the concentrations versus time graph. So we know that hydrogen and chlorine gas will be consumed throughout the reactions. Therefore, they're going to have this graph, this slope of decreasing slope. While for hydrogen chloride, as we know that they are being formed throughout the reactions, and note here that they have coefficients too, so they're going to have double increment in terms of concentrations, and they are increasing. For the second part, we're going to look at differential rate equations. Differential rate equations shows the relationship between the rate of disappearance of reactants and formations of product. When we say relationship, means we're going to combine everything in a formula. So based on the example that we have discussed earlier, we know that we're going to classify them into two types of rate. The first one is rate of disappearance. This rate of disappearance will cater for the reactant parts, while rate of formations will cater for the product parts. So once we substitute into the rate of reactions formula, we're going to get information about individual gases. But is this individual gases can be considered as differential rate equations? No. As for the definitions already states relationships, then we need to combine everything together. Before we combine everything together, I want to explain about the number given here. This number can be obtained from the coefficients in the chemical equations. If we will look at the hydrogen and chlorine, they both got number of mole of 1. So that's why they have 1/1. Negative signs indicates they are being consumed. While for hydrogen chloride, we can see we have number of mole of 2. So that's why we're going to put it as 1/2. So any coefficients that we have in the chemical equations, we're going to put it as the denominator. Once we combine all these rate of reactions, then we're going to get the differential rate equation like this. Now, we want to relate the theory we have discussed earlier to this example. So, given in the reactions, nitrogen gas react with hydrogen gas to form ammonia gas. So, we know already on the left-hand side, we have reactants that will be consumed throughout the reactions, while on the right-hand side, we have product which will be formed throughout the reactions. So the questions already give you the information regarding the disappearance rate of hydrogen. So we want to focus on the hydrogen here. And also the question asks for the formation rate of NH3, means we want to focus on the NH3. So from the information given, we can already tell that 0.30 is equal to negative dH2 over dt. The negative represents the disappearance rate. Okay, how do we relate these two informations together? By using differential rate equations. So from the equations, we can take out the differential rate equations like this. So negative dN2 over dt is equal to negative 1/3 dH2 over dt equal to positive 1/2 dNH3 over dt. So we want to focus only on the H2 and also the NH3. Now we are going to compare these two differential rate equations and then substitute the value. So we can tell that the 0.30 belongs to the negative dH2 over dt. So simply substitute this value and you will get the final answer of 0.20 molar per second represent the formation rate of NH3. Now we're going to look at both rate law and order of reactions. Rate law is an equation that relates the rate of reactions to the rate constant and concentrations of reactants raised to some powers. So there are so many things cramped in here. Let's look at it one by one. In order to write the rate law, we need to have a chemical equations. So given to you this example, chemical equations here, we have reactants of A and B. So how do we write this rate law? We need to first have rate on the left hand side, and then since this rate is related to the rate constant and concentrations, we need to combine it with this equal sign. And then the rate constant is symbolized using K. So rate constant will remain unchanged throughout the reactions. And then followed by concentrations of reactants raised to some powers. So if we can see here, this M and N belongs to the reaction order, or we call it as order of reactions. So this order of reactions shows you how the rate will be affected by the concentrations. And please bear in mind that this reactions order cannot be determined stoichiometrically. It can only be determined by using experiments. So whenever you have stoichiometry, it doesn't mean they are the reactions order for that particular reactants. Next is integrated rate law. So we have already learned about rate law in previous slide. Now we want to do some integrations on the rate law. Integrated rate law shows the relationship between the concentrations of the reactants and time. Let's say we have an example of reactant A to become products. In order to do this integrated rate law, we need to combine both rate law and also rate of reactions. For every example that I'm going to show you, it belongs to the zeroth order reactions. Once we substitute the informations on the chemical equations to the rate law, we're going to get rate is equal to K concentrations raised to the power of 0. Any value raised to the power of 0 will be cancelled out. Therefore, leaving rate is equal to K. From the rate of reactions definitions, we know that rate is going to be negative since A is the reactant being consumed, delta concentrations of A divided by dt. Combining both equations gonna give you K is equal to negative dA over dt. So once we do the integrations, then we're gonna get A naught minus A time is equal to KT, or we can rearrange them to become AT is equal to A naught minus KT. T is the time given, A naught is the initial concentrations. The last term that you need to know for 1.1 reaction rate is half-life. Half-life is the time required for the concentrations of a reactant to decrease to half of its initial concentrations. To determine half-life, we need to substitute this value into the previous integrated rate law that we have done. By substituting this value, we're going to get A naught over 2 minus A naught is equal to negative KT half. So the T and also the AT already been these substitutes. Lastly, we're going to get T half for zeroth order reactions is equal to A naught over 2K. By knowing what is meant by rate law, integrated rate law, and half-life, we're going to see how are they classified into respective zeroth, first, and second overall order of reactions. To see how rate law, integrated rate law, and half-life related to one another, I have divided it into 3 separate columns. The first column will be on rate law, followed by integrated rate law, and lastly, the half-life. As for zeroth order reactions, once we substitute the order of reactions of 0, we're going to get rate is equal to K. Graphically, the K will show that it will remain unchanged throughout the reactions as it is not dependent on the concentrations. Once we do the integrations, we're going to get these two graphs. If we look at the graph, for the first graph, we have positive slope. The positive slope is from this KT. This K got positive value, that's why we have a positive slopes. It is similar to the second one where we have negative slopes. Actually, these negative slopes is determined from the rearrangement of the first equation. So that's why we have negative slope as we have negative K in here. So for the half reactions, you can choose either one of these and then simply apply these substitutions into the integrated rate law. Then you will get half-life of zeroth order reactions is A naught over 2K. So if we look at the graph, the half-life is reduced 2 times. So the first half-life is this much, and when we compare to the second half-life, it becomes this much. So we could say that the first half-life is more than the second half-life, where the second half-life is reduced by a factor of 2. For the first order reactions, we're going to use the same chemical equations as in zeroth order reactions, where A to become products. So we'll start with rate law. We know that rate is going to be K concentrations of A raised to the power of 1. For any of the off reactions greater than 0, we know that the rate going to depend on the concentrations. Therefore, rate is equal to K concentrations of A. While for rate of reactions, we are going to have negative dA over dt. By combining both equations, we're going to integrate them in respect to concentrations and also time. Lastly, we'll get this integrated rate law of ln A naught minus ln AT equal to KT, or we can rearrange them since ln relationship is positive for times, negative for division. Then we'll get ln A naught over AT is equal to KT. Here are the summary for first order reactions. From the rate law, we know that the rate is dependent on the concentrations. So we can see on the graph, we have a directly proportional relationship. That's why the K showing a linear graph. As for the integrated rate law, we know that we can have two versions of them. One is positive slope, one is negative slopes. Both are the same. They are just a matter of rearranging the equations. And lastly, for the half-life, by substituting this value into the integrated rate law, we're going to get half-life of first order is equal to ln 2 over K. If we look at the graph, we could see that the half-life is not dependent on the concentrations. Therefore, they have both equal value of first half-life and second half-life. We're going to use the same example as in previous slide, and then we're going to translate it into the rate law definitions. So rate's going to be Ka squared, okay, exactly the same because they are dependent on the concentrations. And then we have the rate of reactions, negative dA over dt. Once we combine both equations, we're going to integrate them in respect to concentrations and time. And lastly, we're going to get this integrated rate law of 1 over AT minus 1 over A naught is equal to KT. Or you can rearrange them to become 1 over AT is equal to KT plus 1 over A naught. Second order reactions will look like this, where the graph of rate against concentrations of A to the power of 2 will have a directly proportional relationship. And then when we have the integrated rate law, we also have two versions as we have already rearranged them in the previous slide. So both will get positive slope, but then the y-axis differ from one another. And from the integrated rate law, we're going to substitute this value into the equations, and then we're going to get T half of second order is equal to 1 over Ka naught. If we look at the graph of concentrations against time, we could see that the first half-life is less than that of in the second half-life. So means the second half-life is doubled from the first half-life. We were informed at the very beginning that reactions order can be determined only via experiments. Therefore, we are restricted to only these three methods, but we can choose either one of those based on the data given in the questions. First, you can use initial rate. Initial rate is not a graph method, so we simply use calculations. And for the other two, which is linear and also half-life, these two methods gonna involve the formations of graph. So it is essential for you to know the integrated rate law and also the half-life equations for all reactions order. Let's look at an example on how to find the reactions order by using initial rate method. Usually, the questions will ask you to determine the rate law, the rate constants for the following reactions. In order for you to find the rate law and also the rate constants, you must first know what is the reactions order. In order to do that, we need to rely on the data given as below. Given to you a number of experiments from experiment 1, 2, and 3. And recall that we have rate law consists of rate constants and also concentrations of reactants. So we need to focus only on the reactant part. So we have both F2 and also ClO2. That's why the data given is about reactants concentrations. And for the first step, we need to look at the experiments that have the same concentrations for both species. Okay, so for these equations, we have F2. Look at the F2 column. Is there any same concentrations that we can see? Yeah. So from here, we know that experiment 1 and experiment 2. As for ClO2, is there any concentrations that give the same value? Yep. Another one here is experiment 1 and also experiment 3. So it is essential for you to first look at the same concentrations, then only we can proceed to the next steps. Before we proceed with any calculations, we must first write the rate law for these reactions. So the rate law for these reactions is going to be rate is equal to K concentrations of F2 raised to the power of X times concentrations of ClO2 to the power of Y. The reason why we need to choose same value just like before is because we want to find the reactions order separately. So that's why we need to take the same value and then cancel out with one another. So in order for us to find the reactions order for F2, then we need to take the constant value of ClO2. So by keeping this ClO2 constant, then order of F2 can be determined. From the data given in previous slide, we know that concentrations of ClO2 is constant in experiment 3 and experiment 1. So usually, we keep the bigger value on the upper side while the low value on the lower side. So we are going to rearrange them like this, rate 3 over rate 1. So simply substitute all the rate law we have done earlier and then substitute the value. So we could see that there are constants between these two experiments. So simply cancel out the constants, which is the K and also the concentrations of ClO2, leaving only with this value. So on the left hand side, we can get a value of 2 to the power of 1, while 0.2 divided by 0.1 will also gives you 2 but to the power of x. Therefore, we can simply conclude that x is equal to 1, so first order is for F2. For reactions order of ClO2, the same procedure will be done, but this time around, we are going to keep the concentrations of F2 as constants. So, from the data given in the previous slide, we know that we can compare the value between experiment 2 and experiment 1. So, since experiment 2 got bigger value, so we put it on the upper side, while rate 1 is in the lower side. And then we cancel out the constants value, and lastly leaving us with this value. And then we'll get 4 to the power of 1 is equal to 4 to the power of y. Lastly, y is equal to 1, therefore first order for the ClO2. Linear graph method is a method where you need to try and error plotting the data in order to give a linear graph. As long as they are linear, whether they are positive or negative slopes, both are acceptable to determine the reactions order. If you're given sets of data like this and more than 3 data, then you need to go for graphical method to determine the reactions order. You can use both linear or half-life depending on the situations. For linear graph method, we need to use the integrated rate law for every reactions order 0, first and second to get the y and also the x-axis. So recall that we have 0th order of A is equal to A0 minus KT. So we know that our y-axis will be the A here. Okay, so we don't have to change it anymore. So this is for the 0th order. Recall for the first order reactions. Since first order reactions require us to get a y-axis of ln A, then we have to change the informations given here to ln concentrations of N2O5. So the value will be like that. And lastly, for the second order, we know that our y-axis will be 1 over concentrations. Then we have to again add another information regarding 1 over concentrations. So we have done all the informations here. Now we are going to gather them into a graph. We are going to plot them by using this value, separate graph. So once we have plotted all the informations that we have gathered earlier, we will get this shape of graph. So A represents the 0th order, B represents the first order, and C represents the second order. So based on the linear graph method definitions, it requires us to get a linear graph, doesn't matter they are positive or negative slopes. So out of the 3 reactions order, which one do you think will become the reactions order for these reactions? Yes, we know that we have B linear graph, therefore the reaction is in first order. Half-life method is a method where a graph of concentrations against time is plotted. So if you're given questions like these, from the following data, determine the order of reactions, half-life, and also rate constants. It's already states here that they want to find the half-life, then you can simply choose to find the reactions order by using half-life method. Once the graph is plotted, we're going to get this kind of slopes. And then we reduce it to the half of its concentrations, means at 0.5 molar, we're going to get 70 minutes. So this indicates the first half-life. And from the first half-life, we reduce it to another half, giving you 0.25 molar. It will give a time of 140 minutes. This indicates the second half-life. So we know that first half-life and second half-life is equal, which is 70 minutes. Therefore, it can be concluded that this reactions is a first order. We are done with 1.1 reactions rate. Thank you for listening. So you may now proceed to do the NFTF and FTF questions starting from first hour to fourth hour. Thank you.